And then there'll be time later once we start settling into groups, working on projects. Aneesha's put together a really great notebook, and it's confidential and exclusive, but I want to introduce her first. So Aneesha joined LLNL very recently, April 2023, as a scientist with a background in computer science and research. He's working on developing ML frameworks, pipelines, and common data analysis on antibodies and complexes as part of the guide program in the lab. He takes great interest in the interdisciplinary field of bioinformatics, the applications of machine learning, and biology. In the past, her interests included using logic programming to model gene regulatory networks and building models for virtual screening of small molecule drugs. And anything else you want to say before we start? Just thanks everyone. Okay, great. Yes. Thanks. Everyone, good morning again. My name is Aneesha Devulapally. Like you mentioned, I've been in the lab for approximately a year now, working predominantly with 15 public data. Welcome to the WiDS Datathon, WiDS Livermore Datathon, Notebook what? Before we get started, I want to make sure everyone has access to the notebook itself that's been published on the Livermore website. If you don't, just a couple of minutes to go through that. Send out an email with the Livermore WiDS Livermore section, where you can find the node ranker and the data sets to download as well. So that's very active. There are a couple of ways you can work for the notebook. One is with a lab. So link to give the lab as well. So when more with it, you just have to sign again. Search the number. I've already signed them, and all you do is upload them and we'll download it from WiDS. Okay, I'm going to do that right now. Let's just make sure to have the sample data, training of the test data that you downloaded as well, and then take on your runtime. So click the thing for that. If you're familiar with Jupyter server, Jupyter server and how to respond into local system, please do use that as well. Then I'll stop at the end of the notebook. You will actually install anything you want to finish, but you should be able to use the lab shop here. Having said that, I'll get started with the notebook. So, so I'm going to introduce the WiDS datathon problem statement, the data that we'll be working with, walk through some history analysis that can apply in the data, and machine learning algorithms that you can use to fit. During the walkthrough, please feel free to actually drop any questions you have. I also want to check if I'm audible in the for the virtual audience. That a little bit higher. Okay, sorry, awesome. Okay, so beginning with the problem statement, the WiDS datathon problem statement is a classification problem where we'll be working on building machine learning models for predicting the likelihood of diagnosis for a certain type of cancer for patients, if that is less than 90 days, given the information and characteristics of the patients in my data set. The main goal of the problem is to be able to identify or detect relationships between these characteristics, like demographics, condition, where they live, environmental conditions where they live, and the likelihood of those patients getting a timely treatment. Okay, again, if you don't have the data sets yet, you can download it from the Candy website or the Livermore website as well. As with any machine learning problem, we are provided with two data sets, one for training your models and the other just data set for assessing the model performance. Before we get a glance of the data set itself, just if you want to go through the packages maybe you think over today. We're accessing and processing the data, maybe using standard libraries like NumPy and Pandas to store the data in data frames. As a part of the explanatory analysis, we also perform some pre-processing steps on the data for which we use sklearn. sklearn or scikit-learn is a machine learning package Python that provides a wide range of machine learning algorithms and pre-processing algorithms on the data itself. So we'll be using that for building both machine learning models and applying some pre-processing quickly. For visualization and result analysis, we'll use standard packages like matplotlib, cbon, and for some interactivity, we should moving to the data set itself. We start with loading the data set into a pandas data frame. Pandas provides a method called CSV, where it transforms the CSV into the frame form. As you can see here, we see that there are close to 30,000 samples of data points in the training set. Each sample responds to the facial record. So we have 30,000 facial records in the training set and close to 5,000 each country's facial records in our test. The columns here correspond to the characteristics or the information about the patients we'll get into later bit. One point to note here is that the training set has one additional column, which is the diagnosis to get using predictive. Okay. Pandas also provides a useful method called FED, which lets you just get a sample of the data, check the top few samples of the data. That's what you see here for the training data. Each record said is corresponds to one patient, their ID or patient ID. There's information like what race they belong to, what state, their health information like BMI, the cancer diagnosis, code and description as well, where race is all done. We can see additional demographic information like division, region, and it imports to financial information, income. Down, we can also see environmental factors, or information like ozone concentration and abdul. And the final one that you see here is the predictor class or the observation class. Sorry, observation variable. It's a binary classification, so you'll see one and 0, two classes. One corresponds to the diagnosis period being less than 90 days, and zero not. The same is the case with sample test data as well. Test data as well. As you can see, sample on the test data, it's testing information, except for the final column. All right. Pandas also provides useful functionalities and methods to seamlessly access data from the data frame. So if you want to access any specific row, a specific column, or just generate stats or summary of the data that you're interested in, that's possible using steps, as you can see here. LC log lets you access a specific patient record and just accessing the column accessing the column name allows you to get all the information for the column itself, and describe method summarizes. So it's like index the patient index at 25 and corresponds to the patient items getting 4,000, and all the information that is part of the patient is shown here. We can also see the BMI values for all patients that was accessed here, and we tried to print the patient age, summarize the patient age, and you can see that we have patients with age ranging from 18 to a maximum value of 91, with an average age of close to 6. You must have noticed that there are some unknown values as well in the data here. So NaN corresponds to not a number, which indicates presence of missing values. I won't get into the details of the sorts of missing values, depends on how it is selected, etc. But it's important to identify that your data has missing values and also how to handle them. So we plot the heat map using Pandas also provides a method called isInnate, which basically tells us if a particular value is missing null value or not. So the heat map that you see here, green indicates the presence of a value and blue indicates the absence of it, which is there are missing values. So it seems like some data. So the y-axis here is section count and the x-axis corresponds to columns. Right. So you see that some columns in the data have substantially high number of missing data when compared to the others that just have fractions missing in there. It seems like metastatic personal treatment and treatment type have majority of values, but it's not really clear which the columns in it. But this shows that we have. That's the first step. Identify that that's missing data. Another way to represent that is to just count the number of missing data we have in each of the column, and that's shown here. And it's important to know that we're only showing the columns that actually have missing data and not the columns, which is 75 number of columns out of the 3 that we saw. So that's quite a lot of missing data. But interestingly, there are only a handful of columns that contribute majorly to the missing data space in the data that we have here, and the rest are very low value, like 4 or even 1. All the columns just have 1. Another way to represent that is just using the pie chart. So we see that 30% of the missing data comes from the metastatic non-treatment non-treatment type, followed by BMI, patient race, and data type, and the remaining columns are less than 1%. Right? And in fact, the first the highest ones that see here, they have 99% or even more than that. They're covered by missing values. Now that we have established that we have missing values in our data, the next important question to ask or answer is how do we deal with it? There are standard approaches include we can either remove the data points entirely, or remove the columns that have missing values in them, or replace the values with appropriate subset place. Removing the data points would be reducing the number of data we're dealing with. Removing the columns would be missing. We might miss out on some important information that particular feature would deficit in the entire data for each patient. So we want to retain the maximum amount of information that we can as much as possible in the data. So we want to resort to replacing the missing values. But again, the question is how do we replace? What is the appropriate value that we use to replace? But before that, since there are 2 columns where majority it's entirely almost entirely filled with missing data, but there's nothing much that those 2 columns contribute for building the model. So we want to get rid of those 2 columns, and that's what we do. We have remove the columns with highest intrinsic values for patches, and after doing some cleanup, there's an additional column which is patient data, which is one key ways that I just had about moving in the data as well as it wouldn't contribute to the model. So after the cleanup, the number of columns that we left with the training data centimeter, that was 83. The number of training samples, the number of data points removed. For the remaining columns, there is an important point to know is that our data set is a combination of both numerical, which is like continuous values, and categorical, which are not continuous but discrete values. For any machine learning model, it's important to convert the categorical values to their numerical counterparts. But it's a little challenging to do that with missing data. So we'll be dealing with, or we'll be handling the missing data separately for both numerical data and categorical data for that reason. For numerical data, these options could be mean, median or the mode, which is the highest frequency value in the data set. And for simplicity, for calculation data, we first go with the mode value. Other alternatives could be choosing based on other columns, the nearest neighbors and stuff, but we're going to stick with numerical for simplicity here. For numerical data, to pick the best substitute, we're going to use something called box plot. So, box plot is a data distribution plot that summarizes the distribution of the data through their quartiles and also helps us identify any outliers in the data as depicted in the picture here. So, we have a box plot, anyone, I don't know. For all the numerical columns that we have in the data set, I try to focus on the one that's standing out here, which is the three one. Just in order, we use Plotly to plot this, which is an interactive tool, visualization tool, so we can disseminate to just that portion of the plot as well. That's just like. Oh, just hovering over the home value would that. Check. Let's. So all the values that you see on the right here correspond to the distribution of home values in the data set. The minimum value was 60,000 and the maximum value was close to 2 million. That's a huge range, right? However, the median value is shown as close to 250,000. That's a very small value for the 2 million maximum like we're talking about that the data shows, right? With this and also the dots here at the end indicates the presence of outliers in the data, right? Which means that mean of this particular column may not accurately represent the average value and may result in a skewed, the mean would be skewed towards the outliers, right? So the appropriate substitute for our missing value case would be the mean. And this actually applies to the other columns as well. So if I try to any upon this GMI value, take a pen. Needs a few some line of thread. That's the distribution that we have. Minimum of 40, maximum of 85 with a median of 28. So this seems to have outliers as well, and medium seems to be the appropriate substitute for this as well. Just as a couple of notes again. Of course, the scale is not the scaling is not the data is not on the same scale. So we want to reduce the scale for the model to not get biased over that scale data. And since most of the columns have outliers, and then we want to resort because median for as a substitute for numeric. So that's what we do here. We substitute we fill the null values with the median for numerical data. For reducing the scale, I've used an external method called max scaler, which reduces the scale to like an range, and while preserving the distribution of the types, right? And another scaler is like standard scaler, which uses uniform distribution, which make sure the mean and the variance are 0 and 1 for the data. But I wanted to make sure the distribution is sorry, some in like scaler here. You can experiment with scalars, right? And the categorical data is magnetic for that is ranging with the mode, and the label encoder or LLNL for to transform the characters by data into numerical values, which converts them into discrete numerical values. Another important topic or a problem to identify in a classification problem is the class imbalance. Class imbalance problem occurs when the data set is skewed towards one of the classes and compared to the others. And it's important to identify that because you may end up with models that prioritize one class over the other for predictions. So identifying and solving that is an important step. So in our data set, the bar plot here shows that one class is clearly has more number of data points and stuff like the other. So we have class imbalance problem. One way to solve the class imbalance problem is using a technique called desampling. Desampling basically is a technique where we create a new data set from core data set, which now contains a new balanced distribution of classes. IMD-learn, which is short for imbalance learn, is a Python package that provides methods and functionalities for dealing with for applying desampling at dealing with class imbalance problem. It provides methods like random oversampler or undersampler, where oversampling corresponds to increasing the number of minority data points and data points in minority class, and undersampler is reducing the number of class. There's also stratified sampling, which involves creating groups of data points or strata based on common or shared characteristics and sampling from those strata until you exhaust the minimum step. For the purpose of the walkthrough here, I've used random undersampler. Another important note here is that the test data that we've been provided with in the beginning is the one that we use for testing the final performance of one model, and for validating the model or playing around with the models, we be actually splitting the trained data that we have provided with into test and trained subsamples. And in order to keep the distribution of the data as is, and in order to treat the test data as a completely unknown data set for the model, we apply the resampling only on the training set, where we have the train and test. So that's what we do here. We use the train data to train and test splits and apply resampling. After undersampling, the number of data points for each class have been used to take point output. So after the explanatory analysis, the next important concept is feature selection. How do I identify what the right features for my model? One could be the something so but with that, one way to deal with that is manually selecting some columns that it really makes sense from the data slide, right? So think about it. Maybe the health conditions could be a factor for an early diagnosis, the income, financial state of the patient, or the actual cancer cycle step for the contributing factors for early diagnosis. So with that rationale, I actually throw a few columns as features for our modeling. So let's see if they are sufficient for making accurate predictions. We'll start with the logistic regression model. Logistic regression is a machine learning classification model, which tries to predict the likelihoods of an event occurring based on using the sigmoid function and its threshold value. I'm showing the image. So I use the SKLM's logistic regression method to fit the of the features that we've extracted. For assessing the performance of the model, we were saying method or a metric called confusion matrix. Confusion matrix is basically a 2x2 matrix of forms which summarizes the performance of model and contains the number of data points that have been correctly and incorrectly classified in the form of true positives, true negatives, false positives, and false negatives. So in our case, here we're showing the percentage and not the actual ones, right? That's the 6 number. But in our case, the positive class is diagnosis being less than 90 days, and the negative class is not diagnosed less than 90 days. So the true positive block is the bottom right one here. So negative, this is the true negative block. The false positive block is this one, and the false negative block was this one. Right. So things like the model's performance on true positive, the issues, close to a random guesses. I'd say not, maybe not as perfect as in efficiency. Another metric that is used for assessing the model performance is receiver operating characteristic curve, which is a cumulative plot of true positive rate against false positive rate. And in our case here, it's a cumulative plot at different thresholds in now. So for the case of a default threshold of 0.5 for logistic regression model here, we see that the true positive rate is 62 and false positive rate is 27. So that's what we see here, where at a false positive rate of 27, which is somewhere around here, the true positive rate is 62. And the other values are different, the model's performance at different thresholds. So the blue line here indicates a random guesser, where the true positive rate and the false positive rate match at different thresholds. We want our model's performance to always be above the random guesser line or the top left. Sorry. Significantly about it, for it to be a reduction. Area under the curve you see is the area that the curve covers in the receiver operating plot. ROC-AUC is in fact the metric that will be used for assessing the final performance when you submit your results. So this is what we'll be using to compare our model performances. As mentioned earlier, this seems to be close to a random guesser. Area under the curve is 54. Not so great. So the one way to improve the performance is just try other combinations of features that we have. But of course, the number of columns that we have is large, and the size of the columns that we pick is also large. So the dimensionality of the data that we have is pretty big. And so tedious process to actually manage the pick. So we'll be using a method called PCA, or principal component analysis, to actually do for feature selection. In our case, PCA is a dimensionality reduction technique which transforms the higher dimensional data into a lower dimensional space, where the lower dimensional elements, or which are partial principal components, capture the maximum variability in data. And an important point also, QRSI PCA preserves the most important information to the art, fortunately. So we use SQL's PCA method here for transforming our data from the higher dimensional space to the lower dimensional space. PCA for SQL's PCA also allows us to provide the number of components that you're interested in conversion. But for identifying how many components are required, I can choose maximum closure. So when you transform the data, SQL's PCA provides a method called explain variance ratio that that tells us how much variance each component, transform component captures. So the plot here shows that out of all the 83 features, the maximum variance is captured by less than 10 or even less than 5 components, right, in the lower dimensions. Another way to identify that is cumulative variance value here shows that, in fact, just 2 components capture 99% of variance from variability in measured out.
Yeah.
So let's try to use these ACA transform features and fit the same logistics regression model that we built earlier. And the confusion matrix for the same shows quite an improvement in both the true positives and, in fact, all the coordinates, right, where the false positives and false negatives have also substantially dropped. That means, and there is a substantial improvement in the true positives and true negatives. The ROC curve for the same collaborates with that, where the graph what's the top on the right of the history of the has increased from 54 to 77. We'll also be testing out a few other machine learning models, like random forest, which is an ensemble learning machine learning model, which can use for both classification and regression. Random forest is an ensemble of decision trees, where each decision tree is trained independently on different subsets for the training data, and uses majority voting or an average at the end out of the financial screenshots. Again, you're using SKLearn's random forest classifier method to apply the piece and fit the model with the PCA transform data. The confusion matrix for this now does show a slight improvement with comparison of state regression model as well, where non-jump ups and 0 to 7. And the same is reflected on the ROC curve as well, where the ROCA used to reach the accuracy determined that raised the cell. A very interesting feature or functionality that random forest models provides is it allows us to extract what features were identified in the modeling process as important ones that actually played a role in predicting the or in making accurate predictions, right, for this correlated profiles. So we extract the features that are acknowledged as important and try to plot the top 20 features that are right. And the ones that we see here, pair type seems to be the most important features that the model identified, followed by BMI, patient age, patient state, the breast cancer diagnosis score, and the rest. It's interesting because our intuition in the beginning was right, where we said the health could be a factor, the diagnosis, demographics and financial state would be a factor, and the actual diagnosis score itself would be a factor. It's just that it got a contract. So that's what we see here. So that's interesting. Another ensemble model similar to random forest is gradient boost classifier. The gradient boosting, the concept behind that is to transform weak learners, weak learning machine learning models to strong learners by focusing on the points that it got wrong in the clear sequential manner, where there's a feedback coming from different training stems. Again, we're using sklearn's gradient boosting method to fit the model method ECA training data. And we don't see great improvement over random forest, but it's definitely runs over the Dunstan regression model that we saw here, and that is reflected on the ROC curve as well. So as a recap and to compare the different models, this is the RC curve containing all the model performances. The dotted line indicating the random guesser, one for like logistic regression with the randomly selected features, and the remaining good performing ones, of which the best is the green one that corresponds to with random thoughts. I'd also like to actually point out a few other metrics that we could use to assess the model's performance, and especially that would be useful for healthcare data, like ours, right? Which are precision and recall. Precision focuses on answering the question of, as you will see in the picture here, how many of the predicted positive data points are actually positive, whereas the default focuses on answering the questions, how many of the positive instances from the data set were actually predicted as positive. And in one service, the reason it's important for data especially is we want to always try to reduce the false negative rate or the number of false negatives, because incorrectly diagnosing a condition as negative would be detrimental, right? So we don't want to, we always want to reduce the number of false negatives. So by building a model for healthcare with healthcare-related data, we want to do that. So we, as a comparison of all our models, these are new metrics, plus a comparison plot. We do see that the precision, the recall, which is being valued here, does correlate with the accuracy AOC value that we computed as well, indicating that that so far is our best performing model. So before getting into the submission details here, I'd like to take a few minutes to share some tips and tricks on how you can improve your model performance as well. An important factor for in models performance is hyperparameters. Hyperparameters are these additional parameters that models use. For example, in the random forest case, is how many decision trees should I use? What should be the size of each decision tree? What should be the criterion at different decisions, different nodes in the decision trees, right? And so on. There are causing on hyperparameters, correct? So that's one factor. SKNL provides a method called grid search CV, which helps. Of course, there are so many parameters, so options for each parameter, and it's a tedious process to actually, and the comment on HPS is large, right? So it is challenging to randomly pick different combinations of parameters. That job is performed by this method called grid search CV by SKNL. All you have to do is provide the parameter grid of you're interested in and what options for each parameters you want to search on, and fit your classification model. I just printed the results of the grid search to show you the kind of experiments that performs and what you can extract from that. So in the parameters block here, you can see there are 8 parameters that are tested on with different combinations, and each the test score for each combination of those parameters is also presented in the form of an array. The splits here actually then we introduced to another concept, which is cross-validation. Right? Cross-validation is a resampling method where the training data, instead of fixing the test split as one building block, it uses different samples of test split and runs it multiple times in both. And that is what you see here in grid search TV series as the cross-validation grid search. So each new split, there were five. It was a 5-fold cross-validation, which means there were 5 runs with different text samples that was conducted. So each if the here corresponds to those 5 runs, and the values for each parameter of which reality the final mean value basis. If you are sure about the hyperparameters, you could perform the cross-validation yourself using HTML's cross-validate method and directly for the classifier model you're interested in. I've done the same code with the GCA features that we extracted earlier, and the performance for with each of the 3 metrics, precision, recall, and the AUC, show that recall and AUC definitely have they collaborate with the earlier performances that we saw, where the median value for all splits is close to 77. This is just about 77, close to 78. So you can experiment with different combinations with population. That brings us to the end of the walkthrough. Let's go through the instructions of how you can actually submit once you have the final, once you have the best performing model. The test data, you have to perform predictions on the test data that we started off with, that you are doing. So the format in which the predictions are expected is a CSV with 2 columns, one corresponding to the patient record and the other with the action prediction probabilities. It's important to make sure that you transform the test data in the similar way you get on the same kind of pre-processing transformations that we've applied on test train data as well. So that's what we do here at PCA, kind of transform in the lower potential space for the test data as well. The predictions that are expected are actually the probability of the patient getting the timely treatment or not, so not the actual class value. So that's an important one to make note of. All SQL models provide a method called predict proper, which is the probability prediction for a particular of the positive class. So we do the same now. We use our models predict probability function to extract the probabilities for the positive class, and create a data frame with patient IDs and those corresponding probabilities. Fairness data frame also provides this method called toCSV, which converts the data frame and allows you to export it into a CSV form. So you can use the same to save it as a CSV file, and that is the one that we use for submitting. Once you have your results available of your risk performing model, with Datathon website, the Candle website, in the website, you can find the submit predictions option here. When you click that, you can drag and drop the file or actually browse to the CSV file and make your search. That brings us to the end of the demo. If there are any questions or comments, I'd like to answer them.
I just wondering, could you clarify, when you ran the principal components analysis and then the components you used for the logistic regression model, did you just use the first 2 that you were talking about, or did you use them all?
That's a very good question. I haven't used only the first 2. I've used all the components. That's something that you can experiment with as well. So we'll try and see what I just use for confidence is improve my performance. Is the additional components adding noise to my data? That's a very good question. I like it. Yes.
I was wondering if you or anyone in the room is familiar with the relationship between, so we're talking about a diagnosis period. So is it like they go get screened for cancer, but they don't have a diagnosis yet? And then whether they're diagnosed in the next 90 days, is that our economic variable?
So I think, and correct me if I'm wrong, your nose, but I think, so the theme of the problem is equity healthcare. So it's about the facilities that are available for the diagnosis to itself. And 90 days is a range, I think, that where the condition would get for it. So we can do identify if any of these factors are in there, very compound what the space and environmental conditions hinders in any way for them to actually get a diagnosis with that.
Oh, okay. So it's not necessarily like, I'm just trying to think of temporal order here because we're using variables like their actual diagnosis.
Mhm.
And that was confusing to me a little bit.
Oh, you mean if the, oh, I see. I get your question. Okay. The data that we have from police, if I don't that somebody's seen somebody. You're talking about the diagnosis scores for the particular ones and types. Right. So they have been like, it was, I think, the value that shows at the end is if they were diagnosed within 90 days.
Okay. Okay. So the diagnosis period within 90 days happened with, I don't know. I can't wrap my head around predicting the diagnosis period with their diagnosis.
I just want to make sure I understand it correctly. So in our entire population of data, every single entry has the condition,
Right.
right? But it's just certain groups got a correct diagnosis and other groups went undiagnosed.
Okay.
Is that correct?
Yes.
Okay.
Okay. So it could be more about like the type of diagnosis, like maybe the kind of cancer they had might, like that showed up in our model as being one of the, I don't know, it was pretty low on there, but
Yes.
that's what that means. Like,
Absolutely. Yeah. The breast cancer diagnosis is called also contribute.
right. That's making more sense. Thanks. And
Yes.
thank you.
Right, I know it's a nice presentation. So I understand the models are used based on what outcome you want for the data sets. But according to you, for someone who's coming from, Java, Angular, and totally web development world, which model you think we should start with, which is the easiest one, so that, we are just get the whole thing done in a faster pace.
Right. So honestly, it just depends on the type of problem that is given.
Yeah, I do care about just for the learning purpose.
So in fact, the models that that I showed here right now are the basic ones that you can get started with. For example, a logistic regression, which is just a binary classification model to give you an idea of what kind of features you can use to just classify or separate the two classes, right? If you do that correctly or not. And random forest is a slightly sophisticated model as well. And PCA features are the ones that you use to confound features that you have considered depending on the dimensionality. If it's a lower dimensional space, if you just have like 4-5 features, that's the random number. But if you have a very small number of features, you should go with just all of them and try the regression model to see if you can classify or not. There are other methods like SVM, the one that you have mentioned earlier, that you use for classification, and random forest we use for regression as well if you want to predict a particular value instead of a class. And these in fact are the simple ones to get started. So thank you. Another question? Still have 8 minutes.
So the question in the chat is major develops for, such as the AUC for a model to be considered performing satisfactorily for today's problem.
Today's problem. So in the WIDS datathon challenge website, the Camel website actually there's a leaderboard where I think the score that's at top right now is 82%. Yeah. So yeah, I guess that's the cutoff.
Yeah, but I mean, even if you're better than random, that's like, if that's your goal for today, just have to be the best possible in existence. If you have something that's plus learning something new and it's better than a random guess. Then that's so whatever your skill set, that's what I'm 50. Yes. Yeah, I mean, feel free to ask more questions throughout the day. Yeah.